Welcome to a review of gas porosity and aluminium castings. Today, we delve into solidification defects with a special focus on gas porosity. Solidification defects in metal castings can be broadly categorized into three types: gas porosity, shrinkage porosity, and hot tearing or cracks. We will concentrate specifically on gas porosity in aluminium castings. Gas porosity can arise from three main causes. First, gas held in solution in molten metal can precipitate as it solidifies due to reduced solubility. Secondly, if the mold is filled poorly, air can be entrained in the metal stream and get trapped as the metal cools and solidifies. Lastly, sand binders used in molds degrade upon contact with molten metal, producing gaseous decomposition products that can lead to defects known as blows. These gas porosity defects vary significantly in size, distribution, depth below the surface, and form. Let's look into the types of gas defects in detail. The first type of gas defect is caused by precipitation of gas from a solution in the liquid metal. In the case of aluminium, it is particularly concerned about hydrogen. The sources of hydrogen in castings are shown in this figure. The main sources of hydrogen are melting and subsequent handling of aluminium and burning hydrocarbon fuels, such as gas or oil. Gas precipitation from solution in the metal leads to small bubbles, normally in the size range 0.05 to 5 millimeters. It is a result of the high internal pressure of gas due to the microsegregation between the dendrite arms. The bubbles are distributed uniformly throughout the casting, with the exception of a bubble-free surface layer about 2.2 mm deep. The figure shows a typical example of hydrogen bubbles in a simple aluminum casting and emphasizes the size and distribution characteristics. This figure shows a schematic view of a section through a solidifying casting with the mold on the left-hand side. A solidified layer about 1 to 2 mm thick, which is free from gas bubbles, and then the dendritic growth front. As further growth of the dendritic front occurs, we find that small hydrogen gas bubbles are precipitated and become trapped in the dendrites forest. This figure shows the behavior of hydrogen in molten aluminium. Solidification leads to an increase in the amount of hydrogen dissolved in solution of 20 times. Thus, if the initial gas content is 0.1 ml/100, the hydrogen content at the interface would be 2 ml/100 once steady state is reached. This value is above the solubility limit, and thus the liquid aluminium is supersaturated with hydrogen. The final point about gas porosity is that nucleation of gas bubbles continues as metal continues to solidify. This leads to an even distribution with the exception of 1-2 mm, that is the surface of the casting. Now let's move on to the entrapment of air. An example is a sump casting that has been deliberately made badly using a conical pouring basin, a parallel downsprue, and no well base. In addition, we have a non-tapered runner bar and insufficient gates. Such a running system generates surface turbulence in the metal stream as it fills the mold, leading to a chaotic, scrambled mess of metal and air. The air cannot escape easily because it is held in place by the oxide film. Now let's consider the third gas porosity defect, gas coming from cores. The final type of gas defect is blown from cores. When a metal is poured into a sand mold containing cores, the gas present in the core expands and attempts to escape. The gas can escape from the core via the core prints, but if the core prints are too small, or if the mold and core have a low permeability, the gas pressure will build up inside the core. If the pressure reaches the level where it exceeds the opposing pressure of the molten metal, a bubble can be formed in the metal and float up towards the top of the casting. The minimum thickness of the bubble in a liquid aluminium alloy, when lodged under a horizontal flat surface, is usually approximately 12 mm. This dimension is controlled by the ratio of surface tension and density. The diameter of the bubble can, of course, be any size depending on the amount of gas released by the core, and is typically 10 to 100 mm. This table summarizes the various gas defects and emphasizes that they differ significantly in distribution and size. It is most important to bear such differences in mind when trying to diagnose defects in castings, because clearly the remedies will be very different in each case. Thanks for watching. Remember to like, comment, and subscribe.